the last test we're going to look at in this section is the integral test. And suppose that we have this sequence, and we're going to define it as a function that's positive, continuous, and decreasing, okay, for all values where x is greater than or equal to 1, all right? Then if we compare that series to the integral, so we're basically just taking whatever the sequence is, and we're just replacing n with x, and we're substituting it back in, and we're going to take the integral of the limit as it goes towards infinity. Then we can say that either both of the series and the integral both converge, or the series and the integral both diverge. All right, now you can see a diagram below that kind of shows you that, okay, well, if I take the integral, okay, the integral is just the value of the area, okay? But with respect to the sequence, okay, we're just adding up some discrete values in there, okay? So what's happening is the integral is using, the series is using the integral to represent the value, and they're at least somewhat close, okay? So, you know, they're moderately close to one another, but they're certainly not equal to one another, okay? So one thing that we should note is that even if the integral does converge, it is not the value of the series, okay? So let's take a look at a few examples of the integral test, okay? So we're going to use the integral test to determine if the series converges or diverges. And so we're just going to change the n's to x's. So we're going to have now the integral from 1 to infinity of 1 over x squared plus 1 dx, all right? And you probably remember back from when we used our techniques of integrals that this is an improper integral, okay? In fact, a lot of these are going to end up being improper. And so what we're going to have to do is we're going to have to take the limit as c approaches infinity from 1 to c of 1 over x squared plus 1 dx, right? Now, the good news is this is a really basic integral. There's no substitution necessary. There's no integration by parts. It's just an arctangent. The antiderivative of 1 over x squared plus 1 is arctan. So we have the limit as c approaches infinity of arctan of x from 1 to c. And now we can substitute c and substitute 1 back in, okay? So we get the limit as c approaches infinity of arctan of c minus the arctan of 1. Now, again, we have to make sure that we can evaluate these, all right? And we've seen in previous videos several times that the arctangent of c as c approaches infinity is going to be pi halves. And in fact, earlier in this video series, we saw that the arctangent of 1 is pi fourths, okay? And we know that if we were to subtract these together, we would get pi fourths, which means that the integral converges, okay? So this right here converges, okay? And that's because we ended up with a real number in pi fourths, okay? And so because the integral converges, that means that the series also converges, okay? So that's the integral test. We just take the integral and we see whether or not we get a real number for that integral, okay? There we go. Okay. All right, another example. Instead of having 1 over n squared plus 1, we have n over n squared plus 1. We're going to do the exact same thing, where you're going to take the limit as c approaches infinity, right? And I'm going to go from 1 to c. So notice I just jumped right away. I got rid of this first step, so just to save us a little bit of time. And instead of n, I'm going to replace that with x over x squared plus 1 dx. For us to be able to evaluate this, this is a u substitution, okay? If you really wanted to, you could use a trig sub, but nobody really wants to use a trig sub. So we're going to have u is equal to x squared plus 1. The derivative is going to be 2x dx. Okay, that's really close, right? We have x, we have dx, but we don't like that 2, so we're just going to divide. So du over 2 is x dx. And so now we can rewrite this as the limit as c approaches infinity. I'm going to change the bounds from 1 to c to a to b. And we're going to have, instead of x dx, that's going to be du over 2. And then instead of x squared plus 1, that's going to be u. If we evaluate this, this now becomes the natural log of u times a half. Right? So this is going to be the limit as c approaches infinity of 1/2 ln of u. Now, technically, it's the absolute value, but we don't need the absolute value because remember, we're going from 1 to c. All right, and that's not going to change our domain. But if you really want to put the absolutes in there, that's fine. Okay, so this is from a to b. We're going to back substitute. So now we are going to get the limit as c approaches infinity of 1/2 ln of x squared plus 1 from 1 to c. And so now we're going to substitute c and we're going to substitute 1. So now we're going to get the limit as c approaches infinity of 1/2 ln c squared plus 1, right? And then we could just subtract out 1, so we don't need the limit for that one, all right? And that's just going to turn into, make this look a little bit better, okay, minus 1/2 ln of 1 squared plus 1. All right, now we know that as the ln function gets bigger for c, or for x in this case, then so does the y value. Okay, so if you guys want, you remember that the regular ln function looks like this, and it just keeps approaching infinity. Okay, so we know that this animal right here is going to go to infinity. All right, doesn't matter what the other thing goes to, although it's going to be just 1/2 ln of 2, which is infinity. All right, now what does that mean? Well, that means that this series diverges. Okay, and it diverges because infinity is not a real number. Okay, it's a theoretical value. Okay, so it's not an element of the real numbers, and because of that, it diverges by our integral test. Okay, all right. So a couple examples of our integral test, and of course we're going to do a few more of these. Okay, but these are the basic ones that we can look at for now. But again, the technique is you start by going through, you turn the n's to x's, you take the limit as c goes to infinity, and then you just evaluate that integral. If the integral is convergent, then so is the series. If the integral is divergent, then so is the series.